Alrighty, this is chapter 33, and it's just an introduction into masking. So masking is where we use one signal to cover up another one. And this can be done by presenting the masking signal with the other signal, with the probe signal, or there's sometimes you play the masker right before or right after the probe signal. And so yeah, these are just the terminology that you'll see when you're reading the chapter and moving forward. Probe is the signal that's you're trying to detect that's being covered up. And then masker is the other signal that you introduce to try to cover up the probe. So the first kind of experiments with masking, I think, were done by using one tone to cover up another tone. And so they found that when the two tones are very similar in frequency, it was easier for the masker to cover up the probe tone. And then the further and further apart the two tones are in frequency, there's the less masking that occurs. And this is because of the traveling wave on the basilar membrane. So this picture over here kind of shows you how that works. So if you have they use a 1400 hertz probe tone here. This is this like darker colored one, and then the larger gray shaded one is a little bit lower pitched 1200 hertz masking tone. And you can see that when you put these two together, the traveling wave here of the masking tone can kind of envelop the traveling wave of that slightly higher pitched masking tone or probe tone. But if you make these two tones different in pitch, they kind of peak in different places on that basilar membrane, and there's not much masking that occurs. So the masking tone and the probe tone have to be really close in frequency in order for masking to occur. They can't be the same exact pitch though, because that causes this phenomenon called aural beats, which I think they talked about in the last chapter. When there's two tones that are very similar to each other, it kind of gives this beating percept. So you would know that both are there. Wouldn't really be masking if that was being perceived. And it's really hard for a masking tone that is higher in frequency to mask a lower frequency probe tone or masking tone. So I said that confusingly, but so the masker, if it is higher in pitch than the probe tone, then the traveling wave of the masking tone will kind of cut off before it travels down along the cochlea to meet up with that tone that it's trying to mask. So if you look at this line here, so let's say this is our masking tone, and then a probe tone is happening down here that is much lower in frequency. This masking tone is going to, the peak of it is going to stop further down on this basilar membrane, and it's not going to ever reach down here where that lower frequency probe tone is. So there's no masking that's going to occur there. So it's much easier for masking tones that are lower in frequency to cover up a probe tone that is higher in pitch than it. And then there is this concept called critical bands. And a critical band is just the narrowest band of noise that can be used to cover up a probe tone. So now we're not talking about a tone masking another tone, we're talking about some noise covering up a probe tone, which we have found has been pretty effective. And that's what we actually use when we're doing hearing testing to mask pure tones. So the way to find a critical band is they play a pure tone and then play broad spectrum white noise. And then they cut down started by cutting down some of the low pitches out of the noise and then cutting down some of the high pitches out of the noise until they found the narrowest band of noise that they could play that would still cover up a certain tone. And yeah, so that's why we use narrow band noise for pure tones. It contains frequencies right around the pure tone. So you can see here, this is narrowband noise right here, right in this critical band, right outside the probe tone frequency. So it has a little bit of lower pitched energy, a little bit of higher pitched energy. So if you can imagine that traveling wave on the cochlea again, this entire band of noise is playing kind of a really broad wave on the basilar membrane, and it's completely enveloping that pure tone, so it's really good at masking it. And we found that usually it's a fourth to 1/3 of an octave wide that is able to encompass that pure tone and mask it out. So the reason we care about masking is because we would need to use it sometimes when we're doing hearing testing. So it helps us to make sure that we're really testing the ear that we want to be testing. So if you have a very asymmetric hearing loss, you have a lot of hearing loss in one ear and maybe a normal other ear, you have to make the sounds in that ear with hearing loss really, really loud. And sometimes those can cross over to the other side if they get loud enough. And you'll learn more about this, and the different headphones have different tendency to allow sound to cross over. But when we're doing this, when we're playing something really loud in one ear, we have to make sure we're keeping the other ear busy so that when we're playing the loud sounds in the ear with hearing loss, we can know that we're actually getting a response from that ear and we're not measuring any response from sound that has crossed over to the other ear. So yeah, we have to use masking to cover up that tone and keep the other ear busy so that we're not testing that. And yeah, so we use noise because it has different frequencies in it, but it's not a pure tone. We're using pure tone as the signal, so we use noise so that they sound just different enough, so that the person A doesn't get confused about which one they're supposed to be responding to. Yeah, mainly that. And they also have found that if you are masking a probe tone with narrowband noise, it's a linear relationship. So if you turn up the masking noise by 10 dB, you can also turn up the probe by 10 dB. But like I said, you'll learn a little bit more about all of these different methods of finding threshold while using masking in later chapters. But yeah, so what just to really gather from this chapter is what is masking and kind of how does it work on the basilar membrane. And these are just the review questions, a couple of them with the answers from the back of the book. So if there's a 2000 hertz probe tone, would it be easier to mask 1500 hertz, which is lower, or 25,000 hertz probe tone? So the 2000 hertz masker, it will be easier for that one to mask the higher pitched probe tone because the higher pitched probe tone peaks first on the basilar membrane, and then that lower pitched masking tone is going to peak a little bit further down on the basilar membrane, so that traveling wave of that lower pitched masker is going to really encompass that higher pitched peak of the pure tone. And this one says, if a white noise is used to mask a pure tone, are all of the frequencies in the white noise contributing to the masking? And the answer to that is no, because we know that we can cut out those higher pitched and lower pitched sections of the white noise, and just that little narrow band of noise is effective at masking it. So if all the frequencies were contributing, then we would know that if we started to cut down those, if we started to narrow that band of noise, the masking would no longer occur. So we know that when you're playing a white noise, not all of the pitches in that noise are contributing to masking a certain probe tone, which is why we use narrowband noise. And how's a critical band determined? That is just they play the white noise, they cut down the high-pitched portions of the noise and the low-pitched portions of the noise, so they're creating a filter, a little filter of noise. And they just keep cutting down until you find the narrowest range of frequencies of noise that are able to mask a certain signal. And that is everything. So if you have any questions, you can reach out to me or Dr. Bishop, but this is just a quick little overview on what is masking.